Thanks for inviting me. Happy to be here. It's been a while since I've been involved with the infrastructures again in a more active way. So that's why I thought that maybe it's a good idea to first list why I am here. I mean, normally, if you just have a politician on stage, it's usually opening something for 5 minutes, and that's it, because, yeah, I mean, they're usually not in the field. But somehow it has happened that I actually do know the field a bit. I was probably pretty much the first high-energy physics, particle physics experimentator in Estonia back in 2004 onwards. And I actually created the first grid-connected cluster in Estonia, which operated initially from the same room that the Estonian first internet connection was made in, I think, 89 or something. At that time, it was still .su address that was given. So it operated from the same room, and a couple of years later, when we actually built our first data center room, I moved into that room. So I was in that room for, I don't know, 10 years or something. I was also one of the founders of the Baltic Grid collaboration, which started to create the Baltic e-infrastructure for mostly CERN-related work, but it also was looking at a wider field of topics, having biology and others start to use the e-infrastructure that we were creating mostly for CERN, but to allow it to accelerate also other fields of science. I've been a member of the CMS experiment at CERN since 2004. I've actually done actual analysis on the data with the first data until around 2012. After that, I was mostly leading groups and having other people do the work. I did dabble a bit in also analysis in interim, but not as much as members of my group have. And I was also the co-lead of the debugging data transfers. So I know the global debugging of data transfers in 2008, I think. Yeah, it seems there's a small typo. It's not 200 to 2008. It takes time to debug transfers, but not 1800 years. So I know the difficulties of having a global interconnected network of data centers transferring petabytes of data. It is a pain. I'm guessing it's gotten a bit better, but I'm guessing it's still a pain. So large-scale infrastructures are not easy. So any kind of large-scale project is not easy. I've also been a member of the WLCG collaboration board, which handles the worldwide LHC computing grid, but to be fair, I've not been that active in the recent past. I think the recent past is about 5+ years. So. But somehow I'm still listed. We haven't replaced somebody to it. I've occasionally listened in, but haven't been that active. And I was have been the member of the TIES board, so the Estonian research infrastructure since inception. So I have dabbled in the large e-infrastructures, both from the computing side as well as the user side. So I guess that's why I was asked to give this talk. So the parliamentarian stuff is just good for advertising. So let's start first. Where did we come from? In the olden times, or actually oftentimes still today, you have my computer. So it's not just what was on Windows, the access to the files, but it's also that this is my computer. I'm doing the research on it. So it's mine, my own. And this used to be the default case. So getting people to start to share resources was not that trivial. I mean, you might let your postdoc or a student sometimes use it, but mostly it was your computer. You were doing your research on it. You had all your data on it. If it crashed, you lost all your research, etc. So this was how it was normal. I mean, research wasn't work for the weak. But the use for it is mostly minor, in a sense that you can do some minor math in it. You can do some fitting, plotting of the final results, but you don't really do some major computing on it. Although these days a personal computer can be pretty advanced if you stack it with GPUs, etc. But these days also the infrastructures have gotten a bit more huge. So in many cases I've also seen myself from others that the research was actually hindered by the compute power, because a researcher doesn't really want to hand over his computer for 2 weeks of running and then discover that he forgot the save function. It happens, but it's in a lot of cases prohibited by the compute time. So what the researcher usually did was they reduced the scope. Either they reduced the granularity or the size of the field that they were looking at, or whatever they did in their scope, they usually reduced it. So the physics actually, or the science behind it usually suffered somewhat. And in many cases, I mean, these days it's not that relevant, but visualization of all the data running machine learning-based methods used to not be viable. I mean, I did in like 15 years ago, I was doing also some supersymmetry searches in the phase space and simulated across clusters hundreds of millions of points. And then if you try to visualize them to see which regions are standing out, you started to visualize, then went for lunch. And if you came back, you hopefully had a picture, then tried not to resize it, so it wouldn't have to plot all the points again. So it oftentimes was a pain to actually be able to do your research on it. You could do it. I mean, a lot of things could be done on it. Many calculations could be done on it. But it was limiting the actual results. So what are the simple challenges that already start to outscope a local calculation? So let's take a simple example. You need to scan the parameter space for a physics problem with just 2 free parameters. You basically have to define the scales of those parameters and what kind of granularity you want to get from it. So if you take, for example, one parameter has a range of 100 and you need precision of 0.01, and the other one has a range of 2 but precision scale of 0.02, then you discover that you need about 1 million events to map it. Now it comes down to the question of how hard is it to compute per parameter your end result. Might be that it takes a fraction of a second. Then actually a fraction of a second with a million seconds actually is pretty long. So it has to be a very small fraction of a second. The moment it takes like 1 second, then you can do the computation. I mean, 1 day is 86,400 seconds. So from the top of my head, I'm going to say this is going to take, 100 days? A bit more, 120 days? So do you want to spend a third of a year just to see the outcome of that one analysis? If it takes a fraction of a second, of course, you might get done it faster. You might even be able to do it in a week or so. But this was just 2 parameters. Of course, I put the scale down quite small. So normally what you would do, if you can't do this, you reduce the precision. You don't ask for 0.01, you ask for 0.1. You ask for 1. So you get 100 points times, I don't know, 10 points, 1,000 points. You get a rough map. But oftentimes we've come to various scientific discoveries in the tail ends of the distributions. So this is a part where the complexity goes up pretty fast, and it depends on the compute time. I mean, Monte Carlo helps in some, especially like Markov chain Monte Carlo, it can help you with mapping of interesting parts faster. So if you hit a point which is interesting, you can track around it. So you get those results. But this means that you might miss some regions which are also interesting. Again, the science suffers. However, if you decide to expand the parameter space, because 2 parameters is a really easy problem, it might not be unsurprising if you have 20 parameters which are free. I mean, the supersymmetric models, I mean, they only consist of 3 parameters essentially. That's why you can almost never exclude it. So there is going to be a SUSY conference in the year 3000 as well, even though we've tried to exclude it every possible way. So the point is that the moment you start to expand the parameter space, you end up with the problem of, let's say, 1 needs a scale of 10 to the 4, 2 10 to the 8, 5 10 to the 20, and you run out of compute resource for a long time. And okay, let's say 1 needs 10 to the 2, so it just means you get a few more parameters in if you run out of time until the end of the universe, essentially. So the trouble of that is that if you need to increase precision as well, and say you have 20 parameters, it's 10 to 20 times if you need to increase the precision by a factor of 10. So it's a problem, and just essentially exponents a bitch. You can't really work with it naturally. I mean, the moment you try to increase your parameter space, it blows out from you. You just can't work with it in a single environment. So any kinds of these, I mean, scientists are resourceful. I mean, for example, the same example of Markov chain Monte Carlo. So if you hit a spot, just look around it. Maybe it's good. You can do all kinds of tricks, but if you can access more compute resources, you can do better science. This is pretty much the standard outcome. And just a simple example of an extreme case in a large scale where you could in no way do without a distributed E infrastructure is, for example, the LHC. So basically, at the LHC, collisions occur every 25 nanoseconds. That means 40 million collisions per second. Per second. A full event description is about 2 to 3 megabytes. So simple math is it's about 80 terabytes per second of raw data stream. Bytes, not bits. Of course, that is not tenable. Just to remind you, LHC was designed in 1980s with the assumption it starts in 2000 with a data stream of 80 terabytes per second per experiment. Bytes, not bits. The network infrastructure for that did not exist. Not even speaking about the hardware to save all of that. So the first item, of course, was that there is a trigger mechanism built in that tries to filter out from all the chunk that happens the interesting events. And right now it's down to about 500 hertz per experiment. That comes down to about a gigabyte per second. So in a 10 gig fabric, you can pretty much run it full on. And 10 gigabits you can save to storage. Of course, a run normally takes somewhere in the ballpark of 8 to 12 hours. So you have to have the infrastructure to take 8 to 12 hours of continuous data taking at about 10 gig. Again, this was designed in 1980s. They actually gambled that the Moore's law holds when designing a multi-billion-dollar experiment. Luckily enough, Moore's law held, and there were delays. So initially, the rate was about 100 hertz planned, and by start time it was 300 hertz, and these days it's 500 hertz. So there's been ability to add to the compute capability. So you can see, even from that perspective, the technological advancement and being able to build bigger trigger farms has led to more science, because we have 5 times the like frame rate, you could say. This is like a gigantic 3D image maker. So that's about the frame rate, running 500 hertz. So over a year, CERN records about 30 petabytes of data. Yeah, Google has more, right? So it's not a problem per se. LHC has been operating for almost 10 years now. So you're talking about raw data in the ballpark of 300 petabytes. That's doable to analyze through, but now remember that every analysis done at the LHC, and there are hundreds of analyses, thousands of physicists, needs to go through all of that data, plus about 10 times the Monte Carlo simulations to compare it with. So this is this kind of scales where you could not do this if you would not have large E infrastructures. So in these cases, it's an actual enabler of a large experiment, and because of that, we actually found the Higgs boson. So it worked out quite well. It was built for the Higgs. We discovered it in the second year. Everybody's like, yeah, now what? That also explains why I'm now in politics. But anyway, so this is... I'm not a person who looks for a particle's mass precision from 0.1 to 0.01 to 0.001. Not my thing. So it's kind of tough if you discovered a new particle about 2-3 years after your PhD, because normally people discover one per year, per lifetime if they're happy and accidentally lucky. So yeah, happens. Anyway, quickly another example before I go to the challenges and everything. You can also use these large infrastructures to make life possible for the guy with still the My Computer stuff. So for example, in I think that was also around 2008, it was a busy year, a lot of different dark matter models exist. Each have their own particle interactions. Either they interact or they decay. In each cases, they create various cosmic rays, different kinds of spectra. Every single model has a different spectra output. And there are like infinite amount of models because theorists are very inventive. So, but basically if you tune it down from the kinematic point of view, it doesn't matter if you have a collision or a decay, you have a mass spectrum and you have the various outcomes possible. So you can simulate the full spectrum, it just has a lot of free parameters. So these random variables basically mean you have these opening angles, energy distributions, how much goes into which particle. These are all the free parameters of the model. So you can scan them. And then you can do, you can do a few collisions on your computer if you just know exactly that this is my model. This is exactly how it's going to behave. These are the outcome particles. This is the mass of the dark matter particle. I can simulate that. I can simulate 1,000 events or something like this, and I can get an outcome. So if a theorist is going to look for his specific model and wants to make a prediction, he can probably still do it on his computer. I know people actually did it on just their computer. The point is that you are only going to do it for one thing. You have to propagate it properly. You might have the tools for it, you might not. And the papers are somewhat like average or weak. So if you really want to do a proper analysis, you might have to scan the mass range or look for other effects in details, and that's prohibitive for their desktop computers. So what we did was we simulated, billions is probably a too small a number here. To be fair, it's 15 years ago. I don't remember it that precisely anymore. It was a lot of resources that we used on the Estonian research infrastructure and computed and created all the possible spectra, all the possible variations in the spectra, and put it into poor particle physicists' handbook. It's a well-cited paper, because a lot of theorists can now just take their favorite spectra out of it and use it straight out of the box, because they know that their dark matter particle of that mass is going to produce these outcome particles in these proportions. So they take the spectra, mix them together, and they have their output spectrum. So you can do these like common tools, common output data sets, and put the whole data set out there so that all the researchers with their small My Computers can also get their full results at very good precision. So that's why it's a well-cited paper. So it's the data of it is the important part. And it has open data, which is like all the spectra are saved in files, so you can just take them. So e-infrastructures definitely advance science. They give you far more options. There have been far more dark matter models, but that's a good thing or a bad thing. That's a separate topic. But all the physicists who wanted to do it but couldn't now can. So how have we gotten here? So the strive for computing was there already in the 50s. I mean, Feynman is the father of multiprocessing. It was kind of interesting to read that he just made people compute in steps. So the multi-core was multi-brain. So he gave the tasks in sequence to a list of people, and they were just, I know how to compute differentials, I know how to compute integrals. So he just distributed the work and gave in multiple exercises at the same time. So even before computers, there was distributed computing. And the sophistication has gone up through years. And of course, the goal is to make this as seamless as possible for the end user, right? So we started off with just distributed computing. People had different computers in their different locations. That was already a start. Although there is some debate, I would say, if the mainframe was first. Because, I mean, Smaller scale computers were actually harder at the start than mainframes, so they were about the same time. Then came the idea of clustering, that we can put multiple computers together to make a bigger computer. So basically, it's essentially the software stack that made it a bigger computer. Then came the grid, where you not only had multiple computers in one location clustered together, you could make the machine bigger by having them distributed in multiple locations. And you had job scheduling, you could send jobs, you could address a bigger infrastructure. And that's actually what was a necessary environment, for example, for LHC to be feasible. You couldn't do the LHC with just one data center. It would not have been that feasible, really, because that was addressing hundreds of thousands of cores already at the get-go in 2008, 9. So this was something you couldn't do before. Then came virtualization, so you could better manage the different kinds of resources you had on that infrastructure. Somebody needed a Red Hat with specific version. Somebody else needed Ubuntu. Somebody else needs a Windows. Of course, that guy you just push away. But these days, he might actually get resources. So that helped better utilize the existing infrastructure, because different fields, different principalities have their legacy software. So you do need to, and software still is. I don't think you can even now have a Linux where you take out of distribution package and can just install it. That's not been true at least for over like 30 years. So I don't think it's, I think this is part that goes with Linux. So these days you just beat it with Singularity or something. So you don't care about the glibc version being different by 0.1. Anyway, this was old wounds. Then of course came the software as a service and infrastructure as a service. So you could run your stuff in a sandbox somewhere, or you had a software available and you could send your tasks there. I know people have been using like Gaussian or something on the infrastructure, so they can take their Gaussian workload, send it somewhere and get the results back. And of course, the end result is the magical cloud, which just means that you can compute on somebody else's hardware somewhere, and you don't care where. Of course, with that came also the build-up of complexity of the networks, because that is a crucial element. The moment you go distributed, the interconnection network is going to be the limiting factor. Unless your task is extremely CPU heavy and very light on the in and output data. In that case, yes, it's easy. You send your input data somewhere, it computes for 2 weeks, and you get a small output back. You don't really care what the speed is. But these days, for example, also in CMS, you can send your jobs not to the site which has the data, but which has the free job slots. As long as the fabric between the sites is wide enough, you can access the files remotely and just compute. It works. I'm not sure if it's the most optimal way, but it's closer to the cloud concept running on a grid. So it's a mix of that. And when I was looking at the history of the network speeds actually last night, I discovered that we actually had hundreds of gigabits already early in 2000. So I was somewhat perplexed. I didn't remember that, to be fair. So these days we have multiplex networks, and you can pretty much go any speed you want as long as you have enough fibers. So the challenges, because the label of the talk also promised I'll talk about challenges. So I thought, what are the challenges? I mean, first of all, hardware and software stack in a wide distributed environment is always a question, because every single person wants a different thing. We usually have a saying in Estonia that every 2 Estonians have 3 opinions, but it's somewhat similar. That's what I already described, that one wants one thing, the other wants the other one thing. You need also the libraries and tools for parallelizing tasks. Even though this has been a problem for like half a century, I'm guessing it's still somewhat of a problem if you introduce a random new person, like a PhD student, into something. They'll have to learn the parallelization elements. It's non-trivial. It's not that you just give it a task and it automatically distributes and does the computing. Because it's down to how you define your problem. If the problem requires a single system image, if it can be split into various runs, so it depends on the problem. And that's the biggest part. I would say, the user knowledge. I mean, I would say that for a long time, maybe it's better now, but for a long time, if you really wanted to do HPC, you either had to be a CS major or an extreme enthusiast, or both. Helped to be both. So at some point, we were actually looking for particle physics students in the CS track, because it's easy to learn the particle physics stuff once you know all your coding and parallelization stuff. So it's doesn't look like something, I mean, people always say it's not as hard as nuclear physics, right? But in reality, I've seen a lot of nuclear physicists who cannot do HPC. So sometimes it's easier to train it the other way around. So I would say these are the main challenges: to make the environment work for the user and for the user to actually be able to use that environment. Throughout the various projects I've been member of, or the collaborations I've listened in while being in boards or something, it's a common element that we need better tools for the user. We need easier virtualization. We need easier job distribution, better stacks. So this is, I'm guessing, still the case these days as well. I see nodding heads. So I've been out of it for a while, but not that long. So what's the magic goal? I try to visualize what would be the thing we really want. So a computing infrastructure that adapts to the user code base. So you have the hardware, you have the various elements of software on it, and user says that I now want to do this, and that spawns up somewhere. We kind of already have elements of that, but it could be even better. So tasks are understood and split across the underlying compute hardware. So something magical would split the user's workload into manageable parts depending on what the workload is. And the user just has to say, I want this done. Doesn't have to do babysitting of the jobs, resubmitting failed ones, monitoring and fault correction efforts. And then I asked ChatGPT, what would that look like? Sorry, yeah, works with any workload as well, but I asked ChatGPT what would it look like. So that's the magical future. Of course, it took the key buzzword of cloud, literally, but it's interconnected, and you can see that there is still a desktop environment available there, and a lot of people walking on the information highway. So that's the current understanding of large language models, what a magical goal would be. I gave it these inputs, what I wanted. So this is the image that came out of it. It's gotten a lot better. Don't want to know what the original free ChatGPT would have said. So anyway, crashing back to reality. So where are we of that magical goal? We can obfuscate the hardware layer pretty well. I mean, these days you don't really know exactly on which hardware you run. And you don't really care. Unless with an asterisk you end up with something out of the common. So if you want to run on ARM, which is getting a bit better, or you want to use GPUs, you still have to somewhat specialize. It's not that common, available in the common infrastructure. You can't just submit, you have to compile against it somewhat. So it's gotten a lot better. We do have the software as a service, platform as a service, and infrastructure as a service options. So if I just want to run PyLabs or Mathematica or various different services in the cloud, I can. So for a specific software stack, it might be easily readily available with background virtualization. So like Mathematica had already a long time ago a grid option. So somebody spawned the cores in various nodes, and then users just connected to their Mathematica notebooks and they could do their math. And what specific kernels computed it didn't matter to them. So from that perspective, that if you're using a specific software tool and that has integrated into the hardware, you can get a pretty good software as a service environment already. And these days it's also, I mean, through Singularity and other tools, you can get exactly the software stack that you wanted. So you can actually do the software stack in your own desktop environment, and from that create the image that will work everywhere. So I think that's a pretty good advancement over the last 20 years. So it's come users friendlier. So users who know how to set up locally can probably also run it on the grid easier, or on the compute infrastructure easier now. Job management is still a hassle. I haven't done job submissions in the last 4 years. So maybe it's been magically fixed, but I'm guessing that it still is somewhat of a hassle. Somebody still has to babysit. At least when I'm listening in or leading my group meetings, we still have discussions of, yeah, I was running the job babysitter the last few days, and we're probably 50% there, but there's some problems at that site. So sounds like it's still an issue. So we do need to, I mean, specific frameworks exist for larger collaborations because there are some CS majors who are doing the part of taking care of all the complexities of that part, and they try to hide it from the users. I remember the CRAB framework for CMS, where you really just took your physics workflow and you defined a config file, and it tried to do the magic for you. Sometimes. Then new versions of CRAB came and nothing worked anymore. So that's the norm of computing. And it's still a high uptake barrier on how to utilize the HPC. I mean, it comes down also, of course, to the exercise. I mean, can the task itself be split in parameter space? Does it need a full compute image? All of that. So it's a big question. Now, what can and can't do it for us today? I mean, we can share resources very, very efficiently. I think that's the good part. When you have a large HPC center, I'm guessing most of us have a CPU and other resource utilizations quite high in the 90% range. So from the times when the computer cluster was running full tilt for a week, then sitting idle for a while, these times are kind of over. So if you do have resources, it's being shared, it's used efficiently. We can have common libraries, toolkits, basic experts of the splitting of the tasks. What we need to concentrate on is, of course, managing all the new technologies. I only highlighted the word quantum once because I know that the next talk is only concentrate on that. So I'm not going to go to that topic. Of course, trying to get the hand-holding tasks off the users would allow them to concentrate on the science, which would be a good thing for science. So it's something that until we can do it automatically, the educational part needs to pick up more. I mean, we really need our physicists, biologists, etc., to really learn hard computing as well, at least to an extent. So it's something that has to be done. And of course, science will always need more data, more resources. And I mean, the more people start to use HPC, the more complex their exercises become, the more data they will produce, the more data they will need to store. So we will always need more hardware. That's going to be a given. So, and of course, when it used to be that it was a couple of equations, a bit of data, it was easy to just take. I still remember taking data from plots by a tracker where you just clicked on the axis and then clicked on the dots, and you got your spectra. These days, you have complex output data models that you have to put with your paper somewhere. And then you want that data to be available also 20 years from now. That's not a non-trivial exercise. So actually the data preservation and integrity is also going to be a big element of the infrastructures. We use it, but we should use it in a way that we can also reproduce the results afterwards and years to come. So it's not easy. So quick question, can AI help? That's a buzzword, but I thought about this in a concrete way. And to be fair, large language models do allow easy customization of common frameworks for specific user needs. Because, for example, I know a case where ChatGPT was used by a company to integrate that. They gave all the procedural manuals and rules and regulations for ChatGPT, and then they gave their end installation people access to that privatized version. And they could ask in any language, like this was a roofing company. So for example, in this state, how many meters do you have to be away from the chimney to do that? And that varies by state, by regulation, by local municipality. And ChatGPT was very good in organizing data and presenting it in a proper way. In fact, ChatGPT can write CMS software code. So it's very easy uptake for a new grad student to start writing elements. I mean, it's a good learning tool. So it does help in kickstarting tasks. Taking the common repetitive tasks could be something that the AI can help with. So it can adapt to the user's needs if it already knows the framework. So usually these large compute frameworks are pretty well known. So if you integrate it directly into it, it might actually be pretty easy to make it available for users in an easy way. And the users can work in their native language, so translation is not going to be that much of a problem anymore. And of course, this field is developing so fast that it can become more and more sophisticated, and it can actually help in parallelizations and adapt. And basically you could say that the sky is the limit. And just as an example, how many of you, I mean this is wrong crowd to ask it of course, but how many of you can create an Amazon instance and through Singularity run your software on it? Hands up. So even in this crowd, it's only like, I would say, a fifth. So I asked ChatGPT, how could you do it? It gave me all the configurations, commands to run. To be fair, I've never run on Amazon, so can't say if it's 100% correct, but it even gives you the change mode to executable for the run stage. So it's really going to give you all the YAML configuration and everything. So even today, if a dumb user came and said, you just said, that, yeah, just run on Amazon, you would have to explain to that person for a week how to do it. If he's smart enough, ChatGPT answered for me this in just a few minutes. And then I asked to run it on Slurm, I think, and it just rewrote all the scripts. So this, yeah, Slurm. So this is actually configuring Slurm for it. So anyway, so basically this means that these times, I mean, infrastructures are fostering advancements in science a lot. I mean, it's data-intense era. We still, I mean, we can also access, I mean, one of the elements where it helps really is that we can have access to non-standard hardware that we don't have locally. Like these days it's quantum computers, like prototype quantum computers. It's not something every site can have. They're expensive, they're rare, they're hard to run. So being able to access rare resources, and same goes for like large GPU clusters. So these kinds of centralized infrastructures provide an efficient framework, and I think it will definitely always help to advance research, to have these infrastructures available. And I already covered the user training and the data integrity parts. So as my clock ticked into negative, even though I gave myself a bit more time in the end, I asked what would be a nice any questions slide. So this is also out of ChatGPT. It still doesn't get the text right. So infrastructures, I don't know which language that is and what symbol that is, but it's better because GPT-4, this is 4.0, GPT-4 would have gotten like 10% of the text right. So this is 90% of the text right. Even any questions is correct, so it's improvement. All right, so I left some time for questions because I do sadly have to take the life of the politician, so I have a board meeting at 10. But I'll try to be back for lunch, so if anyone also wants to have some private chats, I'll be around for lunch, I hope. But some questions as well now. I think there is some time.
Yes, thank you, Mario. And we are starting our question session.
Thank you very much. Excellent talk and covering so many aspects from particle physics through computing and finishing with AI. Two questions. First one, what do you think about the future directions regarding e-infrastructures and especially the computing facilities for systems like the ones at CERN? So is it worth heading towards the direction that Slovenia took, so more specialized cluster dedicated to physics, or would you be more in favor of some general purpose machines and indeed working on the algorithms to allow all kinds of researchers to access this resource? That's the first one. And the second one, if I may, so you started with the Higgs boson discovery 2012. And then you mentioned that let's see what comes. So what is your opinion actually? What comes, and is it LHC or is it the next facility to work on the topics that we have, like dark matter? Thanks.
So the first question was on specialized machines, yeah. So I would say, I mean, the one thing we see is that at our institute as well, NICPB, 99% of the time the resources are used by the LHC related work. So in these cases where you know that the majority of your code base is going to, or user base is going to be one specialized use, you might want to optimize for that somewhat. You might get just more bang out of the buck. So, but at the same time, if you're like, for example, a university cluster where you know that there's going to be a multitude of users, I would say a bit wider and generalized hardware stack and a very good software stack that can obfuscate it. I mean, you might lose a bit efficiency, but these days virtualization losses are relatively small. We're talking about 1-2% range. So the flexibility of catering to more users is I think, worth it. So I would say it's still a bit of both, in the sense that I'm seeing that like using ARM architecture might be more CPU efficient power-wise for LHC, and we have to scale for high Lumi. We have to scale up so much that I don't think the Moore's law can help us anymore alone. So you need to tackle more things into it. So one of them might be ARM, just because of the fact that you run out of power. And these days, power is expensive. So it didn't calculate into that much, but it does now. With regards to the future of the outcome of LHC, I would say LHC has been running for close to 10 years. I would say most major discoveries would have been made in that energy range by now. So now it's mostly down to a more obscure level of things, smaller rate events where you really have to dig into tail ends of the statistics and get the significances from the data. So I think the goal is free inverse Atabarn. So that, I mean, you might have some results from it, but I think you need a new, first of all, high precision machine to be able to measure the real tail ends of, like, because Higgs is in the metastable location. I mean, the whole standard model is in a metastable space of parameters. So really, small deviations in any directions can mean significant results. So you need a precision machine for that. So either CLIC or ILC or FCC, some of it will be needed. New discovery machine, I mean, whether it's the muon machine in the US or if it's FCCHH, it's way too far in the future. I mean, the next precision machine is only starting in the 30s, early 40s. So the next hadron machine is like 70s, 80s. That's so far out of the way that, well, I'm going to be dead by that time, so it's not a problem. But I mean, you have to train the next generation for it. So that's actually a big second problem. Also, I mean, for computers, it's easier because that's a constantly evolving thing. It's easier to attract new students. For these big machines, it's actually a big problem because you run it for 30 years, 40 years. Then you start designing the next one for next 40 years. So there's going to be multiple generations of people who never actually run on an actual machine, but they have to operate the machine at some point. So it's a tough problem. All right, I think now I've exhausted my time. So if there are any further questions or topics you want to discuss, I'll try to be back for lunch. I mean, it's tough to keep a politician away from a free lunch, so. All right, thank you.